Okay, yeah, and so, yeah, I'm still working on something to do for you for a project. I have it sort of laid out, but I actually had to convince myself that I was right. See, the problem is I used to be smart, so stuff I did a long time ago, it's hard for me to figure out now. So, you know, because yeah, what I wanted you to do, it fits well with all this stuff in Chapter 7 is just build a fancy integral. It's actually what we call an iterated integral, but I had to make sure I was right all those years ago. It's what I worked on my master's thesis, and I was, or well, the better way to put it was, yes, I was right back then, and I figured out again that yes, I was right. So, okay. So I was making some videos this morning. I do want to look at some technical things with Desmos that may help you out at times, and kind of talk about some of the arc length stuff some more, and move into the work section. And I'll get some more the exercises from like 7.4 and so forth. I've been doing some. I just haven't had time to upload them yet. I'll do that this afternoon. So, if you've been working on some problems and getting a little stuck, we can answer questions now, but also you should have some videos you can kind of look at for similar questions later. And so, questions now? Anything? Yes?
Exercise 63 of site 1.4.
Yeah, number 63. Oh yeah, so the length of pursuit. Yeah, let's take a look at that, see if we can get started on that. A fleeing object leaves the origin and moves up the y-axis. So see the figure, we'll draw that. And at the same time, a pursuer leaves point 10 and always moves toward the fleeing object. The pursuer's speed is twice that of the fleeing object. The equation of the path is modeled by, and so they tell us, that's really nice of them to come up with that function for us, because otherwise we'd have to maybe deal with a differential equation or something like that. How far has the fleeing object traveled when it is caught? Oh, nice. Okay. So, this is number 63 from 7.4. So 7.4, exercise 63. Yeah, and so we start here, and it heads up the y-axis. That's the thing being pursued. We start at 10, and we're always heading toward it. So at first, you're sort of heading this way, and then, a little bit of time later, it's there, so you must be heading that way, and so forth. So you should get some curve like this, but again, the way you would build something like that, and maybe we can talk about how this is built. Maybe I'll just save that for a video. But each of these would be a delta t. So how would you build it? Well, you let delta t go to 0, right? And you look at what that is. But you see, we're sort of building that up little bit by little bit, which is what we do with the integrals and so forth. But in this case, they give us that path, and they say that that's 1/3. So y equals 1/3 x to the 3/2 minus, I think it was minus, yeah, minus 3x to the 1/2 plus 2. So that's the curve that we're on. But again, it's a time thing, right? Let's see. How far has the fleeing object gone when it is caught? Show that the pursuer has traveled twice as far. Now, so this problem, this could be a really hard problem, right? I mean, this is what militaries spend lots of money on. This is what NASA spends lots of money on, right? You know, how do you sync up a space capsule with the space station, right? You've got these two moving objects, and you have to zero in on it. These are all guidance sort of problems, and that's a big deal. I mean, there's a lot of science and mathematics, statistics, and so forth that, the physics that all go into these guidance systems. But here, they've kind of let us get around a whole lot of that because what has to happen is I either catch this thing here or I don't catch it. Everybody good with that idea? Right? Is that it's along the y-axis. I have an xy trajectory here that is going to cross the y-axis. So if I don't catch it there, I didn't catch it. I either went ahead of it or I went behind it. And so they make our life somewhat nice because I didn't have to figure out, where that happened, other than I need the y-intercept of this curve. And I know that that's at 2. Okay? So I kind of circumvented a whole bunch of some harder math to kind of get that. And that was the idea the author had in mind, I'm sure, was, we didn't have to start from first principles and that sort of thing to come up with this path. They just gave it to us, and then by restricting this thing along the y-axis, that's the only place we could have caught it. And so I know that I want this curve between 0 and 1 here. Okay. So does that make sense? And so then at that point, how far has the fleeing object gone when it was caught? Well, that, it went 2. Had to, because that's where it is, right? Didn't it start at 0, 0? Or, wait, where did it start? The fleeing object leaves the origin. Yeah, it's 0, 0. And so if I catch it here at 2, 0, it went 2 units. Had to. It wasn't moving around like this or anything. It just went straight up. So I know that the fleeing object went 2 units. So the question is the arc length of this other curve 4 units? Because they want us to show that the pursuer has traveled twice as far. Okay, now with that, is that enough for now? Yeah, okay. So really it boils down to what's the arc length, along that curve between the point 1, 0 and the point 0, 2. Okay. And let's see. Yeah, that's just oh, I just heard something. I just want to make sure. For some reason, yes, admit. Okay. I don't know why it makes me, let people in, but I'll figure it out someday, like January or something like that. But, okay. So, yeah, so that sets up problem 63 pretty well and reduces it to a calculation at this point. Other questions? Yes?
Can we talk about the final?
Can we talk about the final? Yeah, I don't remember, is our final scheduled for Monday and Tuesday or Tuesday and Wednesday? I think it's Monday and Tuesday, right? Yeah. So the latest guidance we've gotten on the final was they didn't even seem to hold us to a time. Because normally what I would do with a take-home final would be to have it due at the end of the final exam period that we have, and that way, if theoretically, if a person wanted to, they could start at the beginning of the final exam period, not look at it at all, right? Look at it at the beginning of the final exam period, do it during that time, and turn it in, if that's what they wanted to do. And that's always worked pretty well. But the latest email I received, it doesn't look like they're scheduling exams actually at a given time. We got something from the registrar that just said, put it on a day, okay? So, in that case, our exam will be due at 11:59 Tuesday night, okay? And I will probably give it to you Thursday after class, okay? And you'll just upload it as usual, and we'll do it that way. So it'll be due Tuesday night, and you'll have, Friday, all day, Friday, Saturday, Sunday, Monday, Tuesday, 5 days plus half a day on Thursday. So 5.5 days to work on it. And it will be heavily weighted toward stuff since the last exam, but it will also have some overarching questions from the whole course. Okay. And beyond that, I don't know. That's about it. That's what I know. Okay. Other questions? No? All right. Took care of that. So along these lines, I did want to point out, I think it's probably worth it to look at exercise 30 from 7.4. So again, just a quick reminder of this with arc length. Pretty much there's one calculation in here for arc length. And I'm trying to remember, now I can't remember if I assigned, 63 was the last problem, right? Was that the,
Was the last one?
yeah. And so, yeah, did I assign surface of revolution? Anything from that? Yeah, I didn't assign anything from exercises 37 through, I guess, 48 or something like that, right? Nothing was from there. We can look real quick, I guess. Module 8, 7.4. Yeah, nothing from there. I just thought we'd not worry about the surface of revolution with the arc length. It doesn't do a whole lot other than add in a 2 pi in there. So go back to, well, yeah, let me go back to, no, that's not what I wanted. Silly. Okay. Go back to this. All right, so I did want to point out exercise 30 from 7.4, so this is 7.4, exercise 30. And this one, it mentions in C the Simpson's rule, but I said use midpoint instead. And now, typing-wise, this isn't so bad if you're typing. When I do the videos, I'm pointing with a stylus on stuff, and that gets old really fast. I do have a keyboard for the thing, but it's a mess to try to combine all that. So here, we're given that f of x is equal to x squared minus 4 squared. And we are asked to look at the arc length on the interval from 0 to 4. Oops. Okay, so every time you do this, I mean, I know what the calculation is, and so in one sense, this is a simple problem. This is, to me, if you're allowed technology, this is knowing the formula for arc length and knowing how to type. Okay, if all I have to do is get this arc length. Because this arc length, say A, is just the integral from 0 to 4 of the square root of 1 plus f prime of x quantity squared dx. Same thing every time. Now, I would say that with technology, oh, well, you also need to know how to take this derivative, but you don't. You need to know how to type it into Desmos and how to type that into Desmos, and it will give you the answer. Okay? So if you do that, I mean, we can get an answer, a very good answer. It's a numerical approximation, but it's probably good to a few decimal places. So let's look at that. I brought Desmos up here. Let me go to projector mode. And so I type in the function f of x equals x squared minus 4 and squared, like that. And you get this very tall, skinny function like this. And, you know, if I just want that answer, that arc length from 0 to 4, I do an integral from 0 to 4 of the square root of 1 plus f prime of x squared, and then come out here and do a dx. And I get 160.28. And let's see, Control plus, make that a little bigger. Okay, so the answer is around 160. And they ask us to do a couple things. So this is part D, is that answer, use the integration capabilities. But notice, you know, that's the neat thing with Desmos is it's not exactly a symbolic system in that, you know, it doesn't take the derivative and use the chain rule and all that. But on the other hand, numerically speaking, it knows what a derivative is, so I can use the math symbols to say, oh, I don't need the function, I need its derivative, and it will numerically do the derivative as well as the integral and the square root and so forth. And just do that, and you get a good answer. I mean, I'm sure that if we could get that analytically, which I'm also sure we can't, but if we could, it would agree very, very well with that as far as just then doing a decimal equivalent of whatever that number is. Okay, so, you know, in that way, from the standpoint of just if you know what the function is, you know what the interval is, and you need its arc length, we got no reason why we can't get a good approximation. I mean, it's that simple to do it. And I, in a way, don't even need to know calculus. I just need to know that's the thing I'm supposed to type in. And somehow it magically gives me that. Okay? So the calculation, straightforward as far as technology. Now, but on this, they ask us to do a couple other things. They say, well, just do the points, find the two endpoints of this interval, and find the distance on that. And, you know, and how might we do some things along those lines? Well, on this, with decimals, probably the easiest thing to do for part A, where we're just supposed to put in 0 and 4, is to do that, just use the distance formula. Let's see, so I just want the square root of the 4 minus 0 squared, and then plus f of 4 minus f at 0 squared. And we get an answer that I might have expected, quite low relative to the 160, the 128. But if you zoom out on this thing, yeah, it seems reasonable that it would be quite low because we miss this bottom part here, because if I can put those points in. So for instance, I can do 0, comma, f of 0. And part of why I'm doing this is to just show you how you can do these things. And so I can just type that in, there's a point. And I could put in my other point, 4 and f of 4. And if I zoom out far enough, you know, I can see them, and I could even go here to change my x-axis, you know, go from like, well, try to go, I don't know, what just happened? That's the weirdest thing I've ever seen. Did that erase everything? Yes, it did. Bummer. Anyway, let me try to do that. Why is that not? There we go. Okay. Go from like -1 to 5. And, okay, now I can get out of there. And, you know, if I do that, and I put those points in, so try that again. I'll just do the points, 0 and f of 0. And so that point shows up, and 4, whoops, and f of 4. Okay, so as I look at that, it seems like the straight line distance between those 2 points should be way, way smaller than the 160. Okay, and it was 130, sounds reasonable. Now, they ask you to do the 4 lengths from 0 to 1, and then 1 to 2, and so forth. Well, that starts getting a little old, okay? Because you know what you need to do, but you got to put it all in and make it work. Well, what are some things you can do in Desmos to maybe make your life just a little bit easier? You can use lists. So, for instance, if I say, okay, I have x1, and that equals, and I do a square bracket, and I do 0, comma 1, comma 2, comma 3, like that, you see it says I have a 4-element list. Okay, now I'm going to go here, and I could do this a couple ways. I could make an x2 that is 1, 2, 3, 4. Okay, that makes sense, right? I'm just going to make the rest, the rest. But these are the left-hand endpoint of each of my straight lines, and I want to make a list that's the right-hand endpoint. So I could put in 1, 2, 3, 4. Well, another way, actually, is to just say x2 equals x1 plus 1. And notice it says I have a 4-element list. What it did was it just added 1 to each element in the first list. So now I have an x2 list that is 1, 2, 3, 4. Okay, now I can keep going with that list idea. I could take the square root of my x1 minus x2, or x2, well, it doesn't really matter because I'm squaring them, but I should be able to do, I think, x2 and then minus x1. Notice it's a 4-element list. Okay, it just took the corresponding elements and did their subtraction. And so I'll square that. And then plus, and I need my f. So f of x2 minus, f of x2, there we go, minus f of x1, and square that. And so there, I've done that distance formula on those two pieces of the two lists, component-wise. So I've got f of 1 minus f of 0, that quantity squared, and then I've got an f of 2 minus f of 1, and that quantity squared, and so forth. So I could do that much quicker that way. And then I still need to know what that list is and add it up. Well, let's pull this sideways so we can see everything. I could either just do it right here, or I can assign it to something like D and then add it up. But all you do to add it up is say total and put the parentheses around it. And you see we get 160.15. We get a number that's really close, actually. So just going with straight line segments between the integers there, we get something that's really close. And I think, let's see. So we could look at, now, because of the way I made the list, I can't get all the points there. I'll either not have the first point or not have the last point when I do this. But just like I made the points before, I could take this and let's say I do the x2, comma, f of x2. And notice, there are 4 of the endpoints. But I don't have the 0 one. I don't have the one at 0. Okay, so these are some nice ways. This list is a nice way to automate things to get it done a lot faster. And then part C says use Simpson's rule. We don't know Simpson's rule. We skip Simpson's rule. But we know the midpoint rule. Okay, and the midpoint rule says, well, you need to take the function at the midpoint and multiply by the width of the interval and add those up. Oh, okay, that's easy. Except you got to be a little careful here. Actually, I made this mistake when I started doing this problem, number 30. The function value we need to add up. Well, remember, if we're using the midpoint rule, oh, I erased it now. Let me put it back in. We were doing the integral from 0 to 4 of the square root of 1 plus f prime of x squared, and then dx. Okay, that's the function we are integrating with the midpoint rule, is that square root function. Oh, yeah. So we would actually need to do that. But again, I can do that. Now, in this case, I need a list of 10. Okay, so I could just go here and make my list of 10, x3, and I just want the midpoints of those intervals. Well, so I got to think about it a little bit. I've got the interval from 0 to 4 divided into 10 pieces. That's a length of 0.4. Well, the midpoint then is 0.2, and then I go 0.4 from that. Now, here's a nice thing about these lists. Similar to Excel, if it knows what the pattern is you're doing, it will fill it in itself. And so, if I put in 0.2, comma, and then 0.6, because I add 0.4 to it to get to the middle of the next interval, comma, and then go dot, 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 comma, and we end at 3.8. So if I knew that already, I can just type it in like that, and notice it says a 10-element list. Pretty awesome. Okay, so just like that. So in this way, right, for your final exam, what can I do? Well, I can ask you, could you find the arc length of something using the midpoint rule with 1,000 elements? Now, why would I do that? Well, one, you probably aren't going to find much in the way on the internet that does that for you. And the other is that you can't do it without technology. And I think it's good to understand a bit about technology. We haven't done a lot with we've done Desmos, done a little bit of Sage Math stuff. But I think if you're going to work with numbers and so forth today, you need to know some technologies. And you may never use Desmos again, but knowing how to use this could help you with something else. So that would be a fine thing to do. Now, honestly, I probably won't do that because the problem is I couldn't really, when you think about it, I probably couldn't really check it very well against the real answer. Because at 1,000 intervals, it would basically be the real answer, right? So if I did something like that, I'd have to be much more creative than just to say do an arc length with 1,000 intervals or something. So, and I'm just not that creative. So, okay, but don't dismiss it as it could never happen. Okay? Could happen. So here I've got my midpoints, and so I just need to evaluate my function that I had up here inside here. So I'm just going to highlight that since I have it already, and whoops, I keep forgetting in here you have to use a Control-C to copy. So I copied it, and then I come down here and I do a Control V to paste it. Now, I need to do this with my 10-item list, so I just go in there and say X3. I've got a 10-element list, so there's my midpoint function evaluated, and now I need to get out here, and each one of those needs to be multiplied by delta x. Okay, and I can either write 4 over 10 or 0.4 or something like that. So, you know, here's my delta x4 divided by 10. And there's my 10-element list, but now if I toss total in front of that whole thing and open parenthesis, I get 159.55, which actually surprised me. Now, the reason it surprised me was that it's not as good an approximation as the 4 straight lines. And I thought, well, you know, n equal 10 with the midpoint rule, I would have thought that was going to do at least as well, probably better than the 4 straight lines. It doesn't. Okay, it does a little worse. So, you know, it kind of goes to show that, you know, intuition only goes so far, and then you're maybe out of luck. Okay, so it did well. I mean, it did very well at 159.55, but it wasn't quite as good as I thought it would be. Okay, but that's some Desmos stuff with lists to make this a bit easier. And of course, also not just the list, but the fact that it will do that numerical integral just by using the symbols. So as long as I put in there f of x, it will do the derivative just fine. It will never show me what the derivative is, but it will numerically work with it just fine. Okay, any questions about number 30 there? Yes?
The change in x, the 4 over 10, does that come from the elements?
On the...
Does the change in x, the 4 over 10, does that come from the elements?
Oh, the 4 over 10 is the delta x part of the midpoint rule. So midpoint rule, I'll go back here. Okay, so with the midpoint rule, the idea is we're doing a numerical integration. So it'd be like a left-hand sum or a right-hand sum, except instead of left or right, we take the middle point, and that was in chapter 4. And so what we're doing is we're going from 0 to 4, and we broke it up into 10 things. I don't know if I got 10 there or not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow. Ha! Something went right. Okay. So this is at 0.4. This is at 0.8. Those are the ends of the interval. So what I did was use my 4/10 for my delta x. So we just did the sum. I equals 1 to 10 of f at, now, you know, here I got to label some things so we know what this means. You know, if I call this x0 and that one x1 and x2, and I go up here to x10, then my midpoint rule says take the x0 and the x1, add them together and divide by 2. And so I'm taking xi minus 1 plus xi divided by 2, and then times my delta x. So the total part, now I could have multiplied that delta x in before I took the total, and I would have gotten the same answer. I mean, we can go back and see if anybody doesn't believe me, but right? Because I can either, since these are all delta x the same value, I could factor it out, and that's what I did. I factored out the delta x, added up the rest, and then multiplied it back in. Okay, so I could have put that inside the total and done it that way, but that's our midpoint rule. But I didn't use that formula. I just went in my head. I said, well, if I'm starting it between 0 and 0.4, that's 0.2, and then it goes up by delta x every time. So that's how I didn't bother computing those that way. I just took the middle. Other questions? Okay. So again, the arc length, for the most part, if you know what the curve is that you are trying to find the arc length of, and you know the values you're going between on x, then it's really a matter of just plugging it in and using technology to get the answer. Now, that said, on video, I tried to do number 4. And as I look at number 4 in the text, my feeling is we should be able to integrate that or find the antiderivative. Okay, once you take the derivative, square it, add 1, and all that stuff. Okay, my feeling is we're supposed to be able to do that antiderivative. I couldn't. So I have to go back. I'm going to go back and make sure I took the derivative right and all that. But I couldn't do the antiderivative, and I think I still have it on here. So that's what Sage Math got. Look at that. It says it didn't know the antiderivative either. Okay, because the integral's still there. It didn't know the antiderivative of that either. So I'm a little confused because I would have thought I should be able to find the antiderivative. Then I went down, I did number 14, and I thought, yes, I found the antiderivative when dealing with that, and then checked the answer with Desmos, and I didn't get the same answer Desmos did. So I don't know, I'll have to go back and look at that one. But number 4, this is one of those things that it looks like, in some ways, a relatively harmless problem in number 4. When you take the derivative, you get this, and that's not just me talking, that's Sage Math, because number 4 says start with x cubed over 6 plus 2 over x, and then I take the derivative and I show the derivative. And there it is, and that's exactly what I got. So I was pretty sure I got the derivative right. Then, you're supposed to take the square root of 1 plus that derivative squared. So that's what I told them to do. And do that integral and show the answer. Okay, the integral from 1 to 2 and show the answer. And sure enough, this is what I tried to do for the integral as well, what I've got, highlighted in there. That is what it can be written as. I had a 1 and I had the 4 under the x squared and so forth. But yeah, you can write this thing this way, and it doesn't know the answer. Can't do it either. So it doesn't actually take a lot to give a problem that you can't do analytically. You have to actually work at it to do one where we can do the derivative. The antiderivative. Okay, so in that way, this section, the idea that, hey, you get it in the formula and you go hit it with Desmos. Yeah, because in real life, if you're trying to do an arc length, you probably cannot do the antiderivative. And it's not just you, it's no one can do the antiderivative. Okay, so so that was just an interesting thing when I did number 4. And again, 13 I'll have to go back and look at because I ended up getting a nice answer for that. I did have to use a technique of integration or getting an antiderivative that we don't have yet. It's actually an algebra technique, so you could argue that we do have it because we're supposed to know algebra, but it's not even mentioned in our textbook until later in the textbook. So, but then I ended up getting a wrong answer anyway, so I don't know. I'll have to go back and look at it. Okay, so that was 7.4 is mostly setting up the integral and then getting somebody else to solve it for you, okay, as in decimals. All right, so let me introduce work. Okay, how many of you have had physics? 1? 2? Really? Wow, okay. So in physics, they have this idea of work. And so this is 7.5. And we're looking at work. And the basic idea is work has a simple definition. So work, W, is equal to force times the distance that force is exerted over. Okay, so F is force, and D is distance. Okay, so the basic idea is, I lift I have a box and it weighs 50 pounds. Okay, pounds is a force. It's actually not a mass. Slugs are a mass. So that's a force. And then if I say pick it up or I'm holding on to it and I carry it or something like that, but I say I pick it up 4 feet, then this just says the work done is 50 pounds times 4 feet, and that is 200 foot-pounds. There you go. Piece of cake. Okay, now, so that is the relationship that we know if nothing changes. But now the question is, well, what if things were to change? So, for instance, you could go with something as simple as, for some reason, suppose I lose 10 pounds with every foot I pull that thing up, right? So, suppose the box gets lighter by 10 pounds per foot. Okay, at a nice steady rate, we'll make it that, so, but it's 10 pounds per foot. Well, see, now we have a problem. Because, okay, I lifted up half a foot, well, it's now lighter, so I don't get the same answer for the next half a foot. and so forth. And so for any you know, if I want to go from 0 to some delta h, right? So this is the idea of just building it up piece by piece. From 0 to delta h, I guess I could use 50. Why not? Right? 50 times delta h. Is that reasonable? It's an estimate, right? As long as I make delta h small, I won't be too far off. Okay, because I'm starting with 50 pounds, and I'm just lifting it that little bit of delta h. It'll get a little lighter, but pretty much I move 50 pounds, you know, maybe an inch or two or something like that. Questions on that? Okay, so then from delta h to, say, 2 delta h, well, I still move it delta h, but it doesn't weigh as much anymore. You know, so how much does it weigh now? Well, now it's the 50 pounds minus 10 times my delta h. Reasonable? Okay, because I'm losing 10 pounds per foot. Well, you know, what was delta h? I don't know. You know, quarter foot, tenth of a foot, a hundredth of a foot, something. But I lost 10 pounds per foot, so times some part of a foot, maybe a toe. That would be part of a foot. Don't even know why I try. But so we've got 10 times the delta h, 50 minus that, that's how much it weighed. Okay, and then I can do from 2 delta h to 3 delta h. And so now that's 50 minus, well, probably 10 times 2 delta h, and then times delta h. Okay, and now I know why you weren't laughing hysterically when I said toe. It's because I see we're over. So, yeah, you tend to lose all sense of humor once you go over the 50 minutes. Okay, so that's where we're going with the work, but notice what's going to happen. I've got my function here, 50 minus 10x, times a delta x. I need to add them all up. It's an integral. Okay, so I'm going to end up with an integral from 0 to 4 of 50 minus 10x dx. And there we go, or h. Okay, so I will see you on Thursday. You can look for the videos and all that. Again, Thursday I'll hand out a, well, I won't hand it out, but anyway, I'll make available a final exam that will be due Tuesday night. Okay.